Alrighty, it's 10 o'clock here in Colorado, and I want to welcome you to roughly our 230th coffee break series from Long Building Technologies. My name is John Stump. I'm a senior sales engineer with Long and have been with the family for approximately 14 years now. We started this June 18th in 2020 as a means to still connect with our customers. So it's been our pleasure to have you on this journey and participating with this. We hope you find it really useful and worthy of your time. Today, I've got Chris DeRoches with me, who works with Swegon BlueBox, which is a product that we are been working with. It's an air source heat pump type of product, air cooled. Today we're going to talk about water volume in that heat pump system and how to allow it to be more reliable. There's a means and a mechanism for the water volume to keep the integrity of the hot water in the defrost mode. So with that, I want to turn it over to Chris. And Chris, if you would.
Hey, thanks, John, for the introduction. Welcome, everyone. Happy to be here for the long coffee break talk for in July here. We're gonna talk today about water volume specific to air-to-water heat pumps and how to think about defrost to make sure that we have good water temperature stability. I was here a couple months ago doing a talk, so just a quick recap for anyone who missed the last session on Swegon. We have air-to-water heat pumps that we've launched last year, two-pipe reversible heat pumps, four-pipe multifunction units with heat recovery to do heating and cooling simultaneously, with heat recovery always happening, even when you have unbalanced loads. These are monoblock package units with 4 compressors per machine, with 2 independent refrigerant circuits. And one of the key points with this that we're going to talk about today is the fact that we're able to defrost those 2 circuits independently. And we'll do an example to show why any heat pump that you're using should have the ability to have multiple circuits and defrost them independently to get much higher water temperature stability. So our product offering ranges from 30 all the way up to 135 tons in a single machine, with controls to coordinate the control and staging of all the compressors in a system with up to 32 units. So this means we can do systems up to 4,000 tons. On the topic of water temperature, just a quick refresher too, these heat pump units have liquid injected compressors. So this means we can do a much higher supply temperature and better supply temperature at low ambient conditions. So today's generation of air-to-water heat pumps, thanks to liquid injected compressors, are able to generate typically 140 water down to 14F and can operate down to -4F with still producing 130 degree water. We compare this to equipment that was on the market 2-3 years ago without injection technology. With what I would call low lift compressors, this means we're not able to generate those high temperatures, so a very steep drop off in the supply temperature as it gets colder outside. So not terribly useful to heat our building through all the colder winter hours, but with liquid injection compressor, the technology is closer in performance to condensing boilers, so that's where the fit is. Maybe next time I'm invited to present, we'll maybe talk in a little bit more detail about sizing, but looking at the weather data for Denver, John and I thought this was important to talk about as well. Most of the heat pump jobs, even though we can operate down to -4, most projects for sizing for 5F, sometimes 14, really size it for the cooling requirement and supplement with backup gas or electric boilers for the other hours. It just comes down to balancing the impact that you're going to have for carbon reduction and energy savings versus first capital cost for the equipment. So really the sweet spot for heat pumps is going to be sizing, for 5F, between 5 and 55F, Denver spends 57% of the year. So this is where all your savings are coming from. So focus on designing for this region and not so much on the colder days. So anyway, how do we deal with defrost? So we talked about controls and defrost the last time that I was here, but we wanted to have more of a focus on water volumes because this is always the number one question. There's a lot of different information coming from different ref organizations, different manufacturers about water volume. So today we just wanted to talk about the physics and how Swegon solutions kind of address that. So as you know, if we're producing heating from any kind of heat pump, in order to extract heat from outside, we need to send refrigerant to the coil outside that's colder than whatever the temperature is outside, so that we get heat to transfer from the air into the refrigerant circuit, and through the work of the compressor, we're boosting that up and making hot water on the outlet. What happens is when it's humid outside, but the refrigerant coil temperature is below the dew point, we're going to have frost that's going to form and stick to the coil. Just like if you open a can of Coke on a hot summer day, you're going to see sweating happening on the can. It's the same thing, but that's happening with our heat pump. So because the coil temperature gets very cold, the worst case that we're actually going to see for defrost is really when we're kind of between 35 and 40 Fahrenheit ambient temperature. Because at those ambient temperatures, we can still carry a lot of moisture in the air, but the surface temperature is below freezing. So we're going to have that moisture freezing to the coil, so we need to get rid of it. So typically we'll do this with air source heat pumps with what we would call a reverse cycle defrost, which is a fancy way to say we're putting the unit into cooling mode for a couple minutes. And to kind of explain this and put some numbers to it, I got a chart on the next slide to show this, and this is really the reason why independent defrosting is very important. By having two refrigerant circuits and being able to defrost them one at a time, we can mitigate the effects of defrost that we're going to see. But a key fact that a lot of consultants really don't think about, but it becomes obvious once you think about it a little bit more, is if we have a heat pump unit, we know that as it gets colder outside, our heating capacity is dropping as it gets colder. So the colder it is, we lose capacity. If we have an air-cooled chiller that's running, right? We take a 100-ton chiller, we rate that 100-ton chiller at 95 Fahrenheit ambient. But we don't defrost when it's 95. We defrost when it's 35, 32, 23 ambient outside. So you have to ask yourself, what happens to the capacity of an air-cooled chiller as it gets colder outside? Does their capacity go up or does their capacity go down? Where capacity increases, it becomes a lot more efficient at rejecting the heat. It's running at lower condensing pressures, so we get a lot more capacity out of it. So when we look at the individual capacity, this example here is our 135-ton machine. And when we look at the rated capacities of each circuit, what they're doing in the moment that we're defrosting when it's 23F outside, because the circuit that's defrosting, it's in cooling mode. So, but we don't get, these are about 65 nominal tons. We get more capacity, 20% more. So this circuit here is actually pulling 75 tons of heat out from the system. And because our heating capacity on the heating side is lower, we're only supplementing 52 tons of heat. So even though we're defrosting independently, we're still producing about 23 net tons of cooling in this moment that we're defrosting for 3-4 minutes. So visually, if we can look at this at a graph, it might kind of help illustrate. So this is looking at what each circuit is outputting as a function of ambient temperature. So you actually see in this chart, it's at 49 Fahrenheit where they actually balance each other and cancel each other out. As it gets colder, our capacity goes up slightly from the circuit that's in cooling, and the circuit that's in heating, our capacity drops off because we lose capacity as it gets colder. So if you look at minus 4F, we have roughly 450 net MBH of cooling that's taking place. So this chart here is actually showing the net cooling output. So this bottom example is what we're actually, the sum, whenever you look at if you're net cooling or heating on this chart, this is the difference between the two. So they're canceling out right at 50 Fahrenheit. As it gets colder, we get more and more and more net cooling. So at minus 4, when we're defrosting, when we take that all into account, we actually have 40 net tons of cooling at that worst case condition. At the top here is just showing what would happen if the entire machine went into defrost. So you can see that if both circuits defrosted at the same time, we'd be producing 160 tons of cooling energy in our system. So independent defrost is definitely a lot better. But this is even the reason why we need to have generous water volumes in our systems. So what happens if you have 4 units and they defrost at the same time? And even if you have 4 units defrosting at the same time, we could be pulling out 60 tons of heat from the system. But really the key with a water volume and buffer tank that we have to figure into our calculations as well is we have loads in the building that are connected to the water loop that are still drawing heat. We have air handlers, fan coil units, coils they don't care what water temperature we have going through the system. They just have valves that are opening and asking for more water. So we also need to factor this into our calculation. Without going into all the turbo math, really what it's about energy in and energy out. So how much net cooling capacity is happening from the heat pumps being on in defrost? How much are the other heat pumps that are still able to provide heating adding back into the tank? And then how much energy are we losing from the system? So we look at the total energy flow. What's the net energy? And if we know the maximum time duration of defrost that this is happening for in the worst case condition that we want to size for, we can figure out the volume that's required to limit the temperature drop in the system of X degrees. So at Swegon, we group this into what we call temperature stability levels. So we would call it low stability, medium stability, or high stability. So in other words, for a low stability, we size the volume such that in the worst case of defrost, we only see a temperature drop on the system of X degrees. So for a low stability, X corresponds to about 15 Fahrenheit. For a medium stability system, we size the water volume such that we only see a worst case temperature drop of 10 degrees Fahrenheit. We almost never size for high stability. It just results in way too much water that's needed. Generally speaking, the more water volume you have, the less impact you're going to have to temperature. But as consultants, you're trying to find a balance between space, weight, and costs, and trying to keep the architects happy in terms of space. So rule of thumb, low stability. This is good for most comfort applications anyway. You're in the range of 7 to 8 gallons per ton. Medium stability would be more in the 10 to 12 range. And as you can see here, high stability is 20 plus gallons per ton. It's just way too much water. So a lot of times we'll do a sizing calculation for a customer. We'll provide a calculation for low stability, medium stability, and oftentimes engineers pick something somewhere in between. So that's just the physics of it. It's not unique to Swegon. It's just net heating cooling capacity for the duration of defrost and what temperature change will that influence. I think the last time that we did the coffee talk, we did talk about some of our control solutions. So we have a water volume tool that we'll provide. It states the assumptions and the conditions that we've calculated all this based on. And we'll actually provide two values. One of the values is if someone else is controlling the units or if we're not optimizing for defrost. We talked about the last time how we can coordinate defrost of multiple units, similar to what we saw in that example with 4 units, all defrosting at the same time. Swegon's controls prevents that to mitigate it as much as possible. So if it's controls by others, though, you can't prevent every single circuit from defrosting at the same time because it's a safety function at the end of the day. So we'll provide that value, and then we also provide a value whenever you're using our controls to optimize and reduce defrost. And generally, we're able to reduce the volume by about 20 to 40% because the likelihood of multiple circuits all defrosting at the same time has been mitigated. So if you're curious to learn more, I'd be happy to set up a lunch and learn on the topic of defrost and water volume with the team at Long Building. And of course, whenever you're doing designs or calculations, selections, that should be a question to ask because it's very important in the early stages of the project to reserve enough space for the buffer tank so that it's not coming at the very end of the project and surprising everyone. Last point I would make on water volume, we tend to use the term water volume or buffer tank kind of interchangeably, but when it comes to these heat pumps, really what it's about is inertia. It's about thermal inertia, having enough connected volume to the heat pumps that can flow through it so that we can buffer what's happening during defrost. So you do get a credit for water content within the pipework, depending on the type of system that you're using. So if you're using a full variable primary system where the heat pump units see the water volume through the whole system, you get a credit for the water volume contained in the piping, and generally that will be significant so we can reduce the size of the buffer tank. When you look at a primary secondary system or variable primary, variable secondary, or even a heat exchanger decoupling, what we would consider water volume for minimum water content purposes is the primary volume, because it's all about making sure that you have enough heat within the system to work for the units to complete defrost. So you don't necessarily have, under all circumstances, full flow on the secondary. So there's different strategies that can be implemented. It's not so easy to provide a black and white rule. It really depends on the application and a variety of conditions that we're concerned about designing to ensure that we're protected with enough water volume. And the folks at Long can definitely help you out with those recommendations and design criteria. So just thought it was important to mention, about piping will influence your water volume sizing as well. Finish it off on a fun note. This is a project Swegon did in Finland. This is a 9 megawatt system, something like 4,000 tons of heating capacity. It's a large data center. They're recovering heat and boosting the temperature up for a district heating system and selling that to homes. But anytime we complain here about buffer tanks, just be thankful that we're not designing these big systems with heat pumps, because this big tank at the back, this is the buffer tank for the system. So I thought at first this was a oil reserve tank for the generators, and they said, no, this is the buffer tank. I think it's 65 million liters of water. So water volume is real. It's the physics of it. But with good control solutions and good system design, we can mitigate that and still make sure that we have stable water temperatures that's being distributed throughout the building. And with
Thanks
that,
again,
I'll pass
Chris.
it back to John.
Thank you very much for joining us, Chris. I really appreciate it. Thank you, BlueBox and Swegon. So our next coffee break is, of course, next Thursday. It's going to be with Weston Broberg. It's going to be talking about commercial laundry exhaust. These are our prizes for this week. We got a beer infused rubs, a 6-pack beer holder, and then a Go Play $100 gift card. And thanks again for joining us on this week's 230th roughly coffee break. Take care. Thanks, Chris.
All right. Thanks, John.